Continuing our discussion of carbohydrate stereochemistry brings us to the topic of anomers. So if we look at D-glucose in the cyclic hemiacetal form, we now know that this structure is the beta pyranose form. We see that C1 is now a stereocenter. Okay, so recall that C2, C3, C4, and C5 were stereocenters in the open chain form, but now C1, the hemiacetal carbon, has now become a stereocenter. It's got 4 different things bound to it: the hydrogen, which I'm not showing explicitly, the oxygen of the ether, the OH, and then the carbon of the rest of the ring of the molecule, are the 4 different things. So C1 has a special name, and it's called the anomeric carbon. And the formation of this ring can result in either of 2 anomers, where anomers are defined as stereoisomers at the anomeric carbon. So if the OH is equatorial, as it was in the first structure I drew, we call this the beta anomer. The other structure with the OH group occupying an axial position is called the alpha anomer. So which anomer gets formed from the open chain form depends on which face of the aldehyde gets attacked from the C5OH. So if the aldehyde is in an equatorial position, as shown here, then when you attack it, the OH ends up equatorial, and the beta anomer will result. Now, I put equatorial in quotes because while you still have an aldehyde, it is, of course, still a straight chain and not a ring, but I have it drawn in the suggestive conformation on the way to forming the pyranose, and therefore I'm quote-unquote calling it equatorial because it's going to end up equatorial. Contrary-wise, if the aldehyde, if we rotate about the C1-C2 bond so that the aldehyde oxygen is now pointing down into a quote-unquote axial position, once you form the hemiacetal and close the ring, the alpha anomer will result. This brings us to the question of, can alpha become beta in any way? And the answer is yes. So the alpha and beta forms are in equilibrium with each other with the open chain form as an intermediate. So the process of converting one form to the other is called mutarotation. So we know that for glucose, there is 64% beta form and 36% alpha form at equilibrium. We already discovered that there is less than 1% of the open chain form for glucose. And that's because glucose likes to form this 6-membered ring, because in the beta form, all of the OHs can be equatorial. In the alpha form, one of the OHs is axial, which is less favorable than all of the OHs being equatorial. But when you think about it, an OH is just not a very large group. So 2-to-1 ratio of it being equatorial to axial is something that we would reasonably expect. This ratio differs for different sugars, and actually for some of them, depending on what all of the different substituents and the configurations of the different groups positions is, for some of them the alpha form will actually be favored at equilibrium. So how do we know this? How do we know that it's 64% beta and 36% alpha? How do we know that these forms are actually in equilibrium with each other? Well, the piece of experimental evidence that we have to support this conjecture is optical rotations. So the alpha and beta anomers, being essentially diastereomers of each other, have different melting points and optical rotations. So the alpha isomer has a melting point of 146 degrees and an optical rotation of positive 112 degrees. whereas the beta isomer has a melting point of 150 degrees and an optical rotation of only 18.7 degrees. So you can see how a small change in structure can make a huge change in the value of the optical rotation. Well, no matter which form you start with, and you can get both of these forms in the crystalline solid state, if you dissolve it up, you will get a solution with an optical rotation of positive 52.7 degrees, which happens to be the weighted average, 64% beta, 36% alpha, of the optical rotation of the two anomers. Okay, so this is direct experimental evidence that we have this mixture of anomers at equilibrium, and that it has an optical rotation that is intermediate between the two of them, because some of the molecules in solution are giving rise to the large optical rotation of the alpha, and others are giving rise to the small optical rotation of the beta. Okay, so having discussed alpha and beta and anomers, the next thing that we want to talk about is one more way of drawing sugars. We've already learned about Fisher projections, but one more way of drawing sugars is what's called the Haworth projection, that makes it easy to see the cis-trans relationships between the various substituents around the ring.